Hello everybody, my name is Andrea Martínez Rodríguez, and today I'm going to present the project of modeling deposit procedure for steep tipping veins for the specific deposit of lithium in Coalpe using Surpac. This project was developed in the company Mining Sanak Ovendofe, and it was also my master thesis for the University Monte of León. A little bit of introduction. This Coalpe deposit is the largest known so far lithium deposit in Europe. It is situated in the border between the two regions of Austria, Carinthia, and Styria, and in a mountain range with the same name, Coalpe. The elevation above sea level is between 1,450 meters to 1,750 meters. The lithium occurs in pegmatic veins, which are hosted in two types of rock, amphibolite and mica schist. And so far there were identified a total of 15 veins, which were investigated by several companies which tried to bring into operation and study the feasibility of this project. So a little bit about the general facts of lithium. Lithium is the lightest metal. It has a very high specific heat capacity, and therefore we find between the applications of industrial applications for lithium, we have batteries, which is up to 35% of the use of lithium, which it has a trend to grow in the latest years, mainly because of portable technology and electric vehicles. But also we find ceramics and glass, or other applications like polymers production, or even human intake. The main producers worldwide are Australia, followed by Chile, China, Argentina, and the typical ore content of these deposits is between 0.5 to 2%. The geological conditions where lithium occurs are two types. It can be found in rock types, in rocks like spodumene, which is the case of Coalpe, or also other rocks like clay types like ectorite, and also in brine sources, like can be lakes, salars, geothermal environments. Although all of this and the relevance of lithium, in Europe we find very scarce production. So mainly there's small production in Spain and Portugal and Serbia. However, European Union is the second importer worldwide, and this means 21% of the global market, just preceded by China. So a little bit of the history of this deposit. The deposit of Coalpe was explored already in the 80s by an Austrian state-owned company. This company started with simply geological mapping, geophysical measurements, and once the interest of the deposit grew, they keep exploring with exploration trenches and surface-driven program. With the years, they decided to assess the deposit, creating a decline and creating drifts along the strike of the veins, and also carried out a core-driven underground program. After this, there were also two experimental stops to select what would be the more feasible techniques for mining the deposit. Along the years, there was several changes of the ownership of the mining rights, and already in 2016, the last company wanted to list their resources in the market of Australia, that, as we have seen, is the main producer of lithium worldwide. And for this, this company wanted to use all data and use it to list it in this market, following the today standards. So for this, they perform some channel samples and doing holes mainly to validate this old data that they have already. Okay, so to be listed in the Australian stock market, it's necessary to approve the resources through the York code classification. This York code is a list of standards which allow to make public reporting of mineral explorations, reserve, or resources. Basically, this depends on two parameters. One is how sure we are of our knowledge of the geological conditions, and the other one is how feasible it is to make the extraction. And this depends on technical and economical or other factors. So this York code is a transparent way to inform basically investors, potential investors, or advisors of investors. So the target for this project was stopped here in the resources size, not considering the minerability of the deposit. So what was the goal and the scope then for this project was to develop a deposit model according to up-to-date standards, which would provide the relevant figures, which would be basically the thickness and the grade, so the tonnage and the grade, so the volume as well for this deposit. It was also required to visualize, to have a model that we could look at, and all of this should be inside the background of your complaint. So therefore, we need to also calculate the reliability of our estimations. So therefore, all the data used has to be validated and statistically analyzed. And for this, all data was evaluated in terms of what is the regularity, how well was analyzed, and similarities between different host rocks. For this, it was the need to develop a standard and automated procedure to evaluate the data and extend the model because this is a living project. So new data will come along, new explorations, campaign, new investigations and interpretations, geological interpretations. So it should be a methodology that would allow to grow this model. So a little explanation about how is the deposit. These pegmatite veins come in shape, we could say like veins, like planes, sorry, because they are rather thin. The thickness comes from 0.25 to up to 5.5 meters. But along the strike, the extension is quite long, up to 1.5 kilometer, and also in the vertical direction up to 450 meters so far, because this is the depth that the drill holes could reach so far. All the veins had identified inclination around 65 degrees, and why we say like they are like planes? It's because the thickness when we compare the thickness relative to the extension along the strike is very small. Okay, so during these ownerships of different companies, there were many works of exploration, some more detailed, some less detailed. So we have here some examples. This one is some from the drifting. They performed very detailed documentation, and they took samples of every phase of the drifting, and not only one sample per drift phase, but in several heights. And also they perform many geological mapping. detail, but this was all not in digital form. Let's say it was done by hand manually. So to be able to use all this data, this had to be digitalized and put in the computer. So here we can see one of these geological profiles overlap in Surpack in this 3D visualization with the model of the drifts. And also at the end, all these profiles will be digitalized. So here is where we can remark how important it is to document properly exploration works, because after this is a topic where companies must invest huge amount of money, and if it's not properly documented, this value it will be lost. Also, as a detail, we have here one part of a vein, and we see the ore is represented in yellow, and there is a part where there is no mineralization, and this is what is called interbedding or a gap in the mineralization. We will discuss later about this. So the idea was to bring all this old data to up-to-date standards with very little new exploration works, these twin holes and channel samples. So for this there was an extensive investigation of the data, mainly of the boreholes, surface and underground, and the drift phase sampling. So mainly we focus on two characteristics. One was the grade and the other one was the thickness, as this is what would allow us to calculate the total volume of resources. So for this evaluation of the data, we mainly use some statistical tools, some very simple, like this box plot. Here we have two examples for drift phase samples and some borehole samples. And what does it mean? Just a reference box plot. The line in the middle, this is the median. The upper and lower and upper limits of the box as the first and third quartile. And then we have the whiskers, which are showing the extent of the 1.5 interquartile. So this basically shows how our data is spread and allow us to compare visually two sets of data. Around the median we have some nodes, and these nodes represent the interval of confidence for the median, and when two sets of data overlap, we can say that their medians are statistically equivalent. So there were also used some linear regression for this data comparison, and some statistical tests like Kolmogorov, sorry for my pronunciation, and Wilcon ransom test, and variograms. So we will see now some of more of this data analysis and validation. So there was the comparison between data was analyzed in different labs. So these labs and duplicates of data was compared. Also the influence of geology, how much the values vary depending on the host rock, if it's amphibolite or micaceous. The influence of compositing. So when we have, what we mentioned before, this interbedding, this area of this gap in the mineralization, how much this influence in the total grade, difference between veins, and also a global and individual comparison of the data. So the main conclusions were that the veins which were host in amphibolite had a higher grade, but a smaller thickness than the micaceous. And in general, the statistic comparison between duplicates and new versus old data was satisfactory. So there was also, for example, here we can see the twin holes comparison. And we observed that for the geology, they are very acceptable, the correlation between original or old drill holes and this new explorer in 2016 drill holes. But there is a high variability on sort scale, so this means the chemical or the grade lithium comparison in a sort scale is not meaningful. But on the other hand, on a large distance, the data has a very good continuity, and that's why a competent person assesses the former data as comply with your system. So now we are going to discuss about some conventional modeling techniques. So basically, when we want to represent any spatial object, there are two main ways to represent it. One is using a surface element or a solid. A surface element, we can imagine it just as a boundary. This is so-called parametric definition. And a solid is something that would include volume and has information about every point inside this volume, and is therefore referred as implicit representation. Anyhow, either if we have an element which is a geometric solid or geometric surface, both can be represented with both types of method. So if we have a geometric solid, this can be represented, described by the boundary surface that compose this solid. And if we have a geometric surface, this can be also represented as a surface which would bound a solid element. Sounds a little bit confusing, but not fully. So what is the difference between parametric and implicit function? We can use the example of how to describe a circle for this explanation. So a parametric function, it will define only certain space. So in this case, if we take the 0 to 360 degrees with this function, we will get the boundary of the circle. If we want to represent the same circle with implicit or volumetric function, we would define the whole space. We will define all the points in the space, either outside or inside the circle. So what this means, that if I have my element circle and I want to know what is this point, when I have a parametric function, I don't really know with my function if this point is inside or outside, because not all points are defined. But when I am talking about a volumetric or implicit function, as all points in my space are defined, I will be sure that I'm inside. Okay. So continuing with difference between surface representation and solid representation, we have to remark that the surface method, a big benefit that it has is that it reduces problems from 3D to 2D. So like we have this nice picture of a face. This is the model in the space, and for our representation, it will be just a parametric surface. Also, as we said already, it doesn't need to define all points in the space. So this means for the computer it will be much accessible, much feasible to calculate, especially if we have a big space that we want to define. And it provides information about neighboring, which means neighboring. So we have here the profile of a surface with 3 points, A, B, and C. And these 3 points, if we look at the spatial distance that they have, they are all neighbors. But if we talk about the topological neighboring, so this means whom is next to whom, we say that only A and B are next to each other. C is already quite far. So this is what a surface representation provides as information. If this would be implicit, then we cannot see any topological neighboring. So in the case of solid representation or implicit, this, as we said already, includes representation of all the points in our working space. And what this allowed is to enable very easily queries about how is our space, is something inside, outside, what belongs to where. And it also allows to represent very complex surface, which is not always possible with the surface method. So how is this translated into SURPAC? I didn't mention it before, but SURPAC is a worldwide mining software used for surveying purpose, modeling, and mine design, between some many other applications. So we will focus in two main methods to model. One is the linear interpolation. And in SURPAC, linear interpolation is done by means of triangulation of surface, so therefore it's a parametric method. And this is very well known for the use of definitions of topography. So if we would measure on the field certain points that we know the coordinates x, y, z, then we could apply a mesh of triangles that will linearly interpolate between these points. But also it is used to do cross-sections interpolation. So we will have, for example, a geological cross-section, and we will connect the points with triangles. So this how would this help us? This would provide a better understanding of the 3D space, but it would not give us any information of how is the deposit inside this surface. And also, the other benefit is that we could calculate the volume. So the other main tool for modeling in SURPAC is the use of block model, that, as you can already imagine, is an implicit method. This means that once is defined working volume, working space, all points inside this space will be included in little blocks. These blocks can have an estimated value, an assigned value for certain properties. And the main characteristic is when a block gets an estimation, this estimation will apply to all points inside the block. So this means is, for example, we want to estimate grade, and we say one specific block has a grade of 2.4. This means all points inside this block will have 2.4 as grade. So now the next question is, how do we estimate these values? How do we provide these information? So there is one method which would be manually, but as you can imagine, a block model has many blocks and nobody wants to do this job. So, and it would be also very subjective. There are two main approaches. One would be discrete properties or qualitative. This would be using a reference surface or boundary or something that we can say everything in this area would get this value. And the other method would be numerical properties or qualitative, which is basically using sample data for deducting these estimations. And the question is, how do we apply this sampling data? It's normally done by means of weighting functions. So these functions determine the influence of one sample in a dedicated point. So how much we take the information, how much information we take from each sample to make an estimation. So between these weighting functions, we find two main methods. One is the inverse distance. This is the simplest method that we have between weighting functions, which basically take, as the name says already, the inverse of the distance of a sample from estimated point, normally to the square. So this means the farther is a sample, the less it will influence in the estimation of a point. And the closer it is, the stronger will be its influence. And the other variant that we have is geostatistics, which basically rely on statistical rules which have a mathematical foundation, and these rules depend on the location of the samples. What is the main benefit of geostatistics? That they provide a reliability assessment or a confidence level of our estimation, and they are based on variograms. So here comes what is a variogram. Variogram is a method to represent the regularity of a deposit in the space. So basically it's built as a graph which is calculated measuring the variance of samples with a defined, in this case called h distance from each other. So it would take all the samples with 0 distance and calculate the variance. All samples with 50 meters distance and calculate the variance. And that's how the variogram is built. What means if we get a positive slope, like in this example, this means that the closer the samples are, the more similar are. And the farther they are, the more different, basically. So there is always, or in general, there should be a point where there is a limit, where the variance doesn't get higher because already reached the maximum. And this means there is already no connection with the neighbors, so we don't get influence of the points which are farther than this distance. This will be the range. Another point to look at in a variogram is the nugget. The nugget is this distance between the 0 start of variance and where our variogram starts. It's not always like in this case, it can also come directly from 0. And when we have a nugget, this means that there is variance even for samples with 0 distance. This means that there is a small distance irregularity. So this means that samples which are next to each other already would have different values. So between geostatistics, we are going to look at 2 methods. One is the ordinary Kriging method, which is a linear combination of values that we will create between the samples which are in a defined search radius. This search radius will rely on the data that we saw from the variogram. And it will provide a different weight for each of the samples depending on the distance to the point to estimate. The main benefit is that as the error can be calculated, it can be also optimized. And this all depends on the variogram. And the other benefit is that it provides always unbiased estimations for the mean. This means that the mean of our samples would be the same as the mean of our model. The other method I would like to look at is the indicator Kriging, which makes, instead of giving a value for a block, it would give a radio. So you would express determine a threshold value. Like for example, I say my thickness is 1 meter, and the value, this indicator Kriging would provide what is the percentage which is above and below this 1 meter of each block. If we define several thresholds, we will be able to calculate a distribution for each block. So at the end, the result would be a series of ranges and how often they occur in one block. So next point will be how to decide the size of our blocks. This is directly related to reliability, because inside a block, we say that all the points have the same value. So this means when we have a bigger block, the real variability of the points inside this block will be bigger as well. So we know already there are here points which are inside the deposit and outside the deposit. But in our block, they were all considered like inside. On the other hand, if we have very small blocks, like in this case, what we will have is a lower reliability, because the chances that we are sure that in this block the estimated value is what we have are much lower. It also would have a smoothing effect that will not allow to see any boundaries, because we will get many values with very different value. And it will also be very challenging for the computer, because this would mean much more data to process. So a parallel example to this would be to talk about the weather. So if we want to say which would be the weather here today next year, so let's say the 20th of September of 2021, and I say it would be 27 degrees, the chances that I'm right are very small. But if I say the weather for the whole summer of next year would be, the temperature would be 25 degrees, chances that I'm right are much higher. So this is exactly the equivalent. But although I said it will be 25 for the whole summer, the difference between one day and the next one would be high. So that's why we have a high variability. It's the same that happens in this case. So the chances that the average value that I estimate for here, this 25 degrees for the whole summer, are right, are quite high. But if we compare point to point, we will have a big variability. Okay, so now going back to the CoAlpe project, what are the requirements? So we remember that we have narrow pegmatine veins with 65 degrees of inclination. These veins are relatively close to each other. So if we want to define the difference between one vein and next one, the block size should be quite small. And the main attributes to model could be the lithium oxide grade, the thickness. We should have a reliability assessment of these values, and it should be in a way that admits new data and can be automatized. So here we have a discussion between these two main modeling possibilities that we are looking at today. In one side we have geostatistics with by means of block model, and in the other side we have triangulation by means of linear interpolation. So with geostatistics, what we will have is a full definition of the space, and this means we can apply to estimate the lithium grade. On the other hand, with triangulation, we would have just a pure boundary definition, which could serve to define the host rock boundaries. The good thing that we have seen already of geostatistics is that it provides a reliability value, confidence of level, but also depends on the block size, and we are saying already that we will need a very small block size. But if we go to triangulation, there is no reliability assessment, and this would not comply with your. In the side of geostatistics, we would have direct extrapolation with a statistical background, but for the triangulation, it would be subjective, and based on intuitive assumptions, which is also not in the line with your complaint. For geostatistics, as we saw in the example before, we will have this smoothing effect that will not let us determine the boundary between the vein and the host rock. But on the other hand, the triangulation, we see that it will perfectly fit to our geometry. The geostatistics, it's possible to use this method by programming, so we can automatize it. But triangulation methods are very time-consuming and laborious because basically they are manual. So looking deeper to our situation, we know that in case of the vein, when the vein is going to be mined, it will be mined in the whole extent of the thickness, because it's the distance that we are having in this case from 0.25 up to 5 meters. There is no selective mining good enough to say we take only one part of the vein. On the other hand, we also have very scarce information about how the conditions of the vein change along this thickness. And as we are already feeling, the conventional block model would need a very, very small block, which would make our computer explode, and it would have very low significance or reliability. So therefore is why this innovative semi-2D approach is proposed, which consists on modeling in 2D, neglecting the variations along the thickness. In this case, we can use geostatistics. We would also model thickness as another attribute. This will provide this reliability analysis. The block size will be able to be optimized, and it can be done in a vein-by-vein basis, which would be based on the geological assignment done by geologists to which sample belongs to which vein. So for this, first it's necessary to transfer the data into 2D. So we have here a representation of a vein, and it's intersected by some drill holes, and we have a sample, and the data of this sample will be represented by a point in the central position with the information of the lithium grade, the thickness, or any other information that we want to model. And this would be projected to a projection vein defined for each vein, which should try to be as parallel as possible to the vein. And then this information would be applied to estimate blocks of a 2D model, which would be in the same orientation as this projection plane. So for this, it's needed to get this variogram data. So for this, it was used only drill hole data, because drill holes were drilled in all veins. But for example, these drifting samples, they were done only in a specific vein. So to be representative, we take only drill hole data. And then in this case, we don't have so many samples for each vein. So we decide to use, as we have seen, that there is a good continuity of the deposit independent on which host rock or which vein. We can use all the drill hole data to create this variogram. But we don't want to compare samples which belong to different veins. So for this, all the data, all these points are sampling data for different veins, and they were relocated in the space along a vector, keeping the relative distance between them, but with a distance between vein and vein data, which would be bigger than the search distance for this variogram creation. So the results of the variograms, which were used for both for amphibolite and mica-schist veins, present for lithium a high nugget, which means that on short distance there is a high variability. Then it comes a curve very steep, which means that the short distance relation between samples is not very relevant, and it lasts only 50 meters. But it was observed a second structure of 300-meter range, which means that although we saw already in the short distance there is not much continuity, but there is a good continuity on the deposit for the long range. For the thickness, the data was a little bit more favorable, with a range of 100 meters for this continuity. So all the variograms for lithium and thickness were used for the ordinary kriging technique. And then we had to decide which would be our block size. So the block size should be also related to the sampling grid, so how often do we have a sample, and then mining equipment, so we were mentioning before the selectivity, because at the end, if we are going to extract all together, it will be mixed anyway. So the proposal was to perform blocks of 25 meters by 25, which would have anyway a high variability on a smaller scale, and on the set value would be only 1 meter, because by default we cannot say less than 1 meter in Sulfur, but it's irrelevant. And it will be according to possible mining techniques for this deposit, like long hole open stopping. It will have an area which would remain feasible for mining stops calculation. So for the grades of calculation, we have to consider the interbedding that we mentioned before. So this means when we have in a vein a gap in the mineralization, as this is again too small for computer capabilities, it was decided to be another factor to model. So not only thickness and grade were modeled, but also interbedding. And this interbedding was used as a factor to dilute the lithium grade. So we create a composite sampling grade that will be distributed factor. For the thickness and volume, the thickness was measured as the perpendicular intersection of the projection plane. So here we have our projection plane, and the thickness is something very ambiguous how you consider thickness. So it could be like this, it could be like this. So it was defined as just perpendicular to these projection planes. As you can intuit here already, this would not affect the volume. So the volume calculation would be the same. Doesn't matter how inclined is the projection plane, but it would affect to the thickness of the vein. So it's not depending on how good was the projection plane, how parallel was to the vein. It would make a difference for the estimation of the vein. This difference is calculated as the cosine of this angle of deviation, which would mean for 20 degrees deviation, only 6% of error. So mainly this has a relevance when the data is used for further steps of design or mining considerations. So now we want to visualize, so this was enough already to have the volume calculation, but we want to visualize the results in 3D. So for this, we take, by means of linear interpolation or triangulation surface, we connect all our sampling points in the middle, and we create a surface. This surface will take all the data which was calculated by our model, which will be projected in our surface. And from this, each point with the information of thickness will be duplicated by the half of the thickness to each side. And like this, we will create a vein boundary in 3D, which will be oriented as this projection plane. But the thing is that now we want to sit in the real position in the space, so we have already a 3D structure as a surface made based on triangles. So we have to put it back to the original 3D position, so from the projection plane, it will be moved. And then we want to check how good was our estimation. So for this, we will take each vein and intersect it with the drill hole data for each vein. And if we see that there is a drill hole which intersects a vein in a point, and this drill hole says there was no sample for this vein, but the vein is there, this means there is an error. So that's why there would be an interaction process where in that specific drill hole, in that position where there is the error, it would be included a dummy sample or a sample with thickness equal 0, which should be where there should be a gap. And in this interaction, the model would get the lithium thickness would get reduced in this point, and it would be an objective correction according to this vein assessment. How is it represented? So in SURPAP you cannot have a surface or a solid representation with a gap in between, but we have gaps in our mineralization. So what was done is that both sides of the definition of this boundary would be in the same position. So it would have a thickness 0. So a little summary of how is the modeling procedure. First, samples would be extracted with data for lithium, thickness, interbedding. Also, they will be transformed into 2D. And after this 2D transformation and projection in the plane that we will use for modeling, the modeling is performed according to the variogram. We will use some defined plane limits to limit this extrapolation space that we allow. And then we will check the geometry, creating these two surfaces of handball and football. And we will transfer the data again into 3D, doing this connection between the 3D position of the drill holes and our 3D geometrical model, adding data as zero thickness in the positions where we see that there should not be a vein, but we will model a vein. And with this we will have finished the process for each vein. So after this, the results were a total of 6.3 lithium tons with an average of 1.17 for lithium and 1 lithium oxide, sorry, this is a typo, and 1.3 meters of thickness. So now we have this general result, but still we need to analyze the reliability of this. For this, we would look at the local reliability, the cutoff value, and the global reliability. So for the local reliability, we said that these big blocks are 25 by 25 meters. Inside they include points which, of course, will have a different value than the one which was estimated. This is what we call variability. So as we said before, in geostatistics, we will have values, estimation values, which are unbiased for the mean. So this means if we have the deposit, this blue line here, the mean value would be here, and for our model, it would be in the same mean value. But this doesn't mean that they are unbiased for the distribution. So for the tails of the distribution, they would tend to be closer to the mean value. This means that the high or very small values are underestimated. So this effect is driven by the values of the variogram and the spatial sample distribution. So therefore, it was analyzed the reliability for each block, for the estimation of each block, in terms of the standard deviation. And as we expected, the standard deviation was quite high, like we reached like 16% would be 0.4. This means a high reliability for the numbers we are working with. So that's why it was calculated also the indicator kriging as we explained before, the indicator green would provide a distribution of the grades inside the block. So we want to avoid that the values are all concentrated above the mean. We want to make sure that we also know the distribution of the stream values. This has a lot of importance for the mine design, because we would want to know at the end of the day which areas are feasible to mine and which areas are not feasible because maybe the lithium is too small, the lithium grade is too small, or the thickness is too small. So like this, we will calculate a cut-off radio curve, which will provide a better understanding of the distribution in the deposit. And we can see for the classes that were established, we see in blue the ordinary kriging, and in orange the indicator kriging, and we see that with the indicator we can see the stream values. Not everybody goes to the mean. So after this, what we want to really ensure for the job complaint is our knowledge about the global reliability. So our knowledge about the resources estimation. So we know that for a block, we already saw, as expected, that the variability is very high, but on a global view, we can already assume that the reliability will be much higher. Why? Because the errors are compensated. So areas which have, in reality, a smaller lithium grade than the estimation will be compensated with areas which have a higher grade than the estimation. So for this, it was applied the Monte Carlo simulation. How does it work? So Monte Carlo simulation used random numbers to evaluate how well works a model. So it's based on interactive technique. So you try many times to later measure the likelihood of the results in the model. So how this was applied for the Koral deposit, it was done 100 iterations with random numbers selected from the distribution for each block. So for each block, we have to remember we got a mean value and we got also a standard deviation. So from this, we can create a distribution and extract from this distribution 100 sets of 100 values randomly extracted. The only condition was that negative values were not included because it wouldn't make sense, a negative thickness. And then for each iteration, it was calculated a volume for each block. And then after this, it was calculated the mean value and standard deviation of the set of 100 simulated tonnages. And with this, we could calculate the reliability independent for each vein and for the whole deposit. And for the whole deposit, the reliability is very high. This means that the standard deviation relative to the mean was 0.8%. And this means that the total resources varies only plus minus 100,000 tons with a 95% of confidence. So we can already say that the reliability for the whole estimation of resources is very high. And here we have the conclusions. So it is presented an innovative method combining the best of two modeling techniques. So geostatistics by means of a 2D block model and linear interpolation using it for 3D verification and representation. This is the only connection where the model of such a deposit would have a reliability, could be analyzed, this reliability. And in this case, it was managed that the thickness and the grade were both analyzed and based on statistics, which are values very critical for mine design or overall finance estimations. It was also achieved an accurate 3D visualization which fits to the samples, and all this method had a high level of automatization. This means the incorporation of new data and interpretations could be very fast, and this was also approved by the competence center and assessed by the job complaint. So thank you very much, and I hope it was of your interest, and if there is any question, I'm here somewhere.